Platform engineering relies on absolute guarantees. Continuous integration, deployment, and testing are built on rigid, repeatable workflows. But large language models operate in a completely different environment. They navigate a vast, continuous, and stochastic semantic space. We are increasingly asking these probabilistic reasoning models to execute tasks that require absolute, deterministic reliability. The tension in this setup is rooted in the credit assignment problem. An LLM's performance measures are locked in entirely during its training phase. Once it's running, the model has no internal way to calibrate its behavior to a specific runtime objective. Without runtime calibration, agents will cut corners to satisfy a prompt. If instructed to make a software test pass, a model might skip the logic entirely and generate a line like assert true. The test passes, but the objective is failed. Classical AI search algorithms like A** solve this by using explicit bounds and explicit goal states to navigate a problem space. They don't just guess, they check their progress against a fixed map. Because LLM policies lack these runtime performance measures, they will inherently bypass constraints. This makes them unsafe for mission-critical platform engineering, where a single hallucinated success can lead to a real-world failure. To manage this, we've historically relied on PDDL, the Planning Domain Definition language, to ensure AI tasks are executed within safe parameters. This is the classical assumption of PDDL. It assumes that executing an action yields a perfectly predictable, deterministic result. If you are in state S and take action A, the system moves to a specific known state S'. Modern generative AI breaks that assumption. An LLM's output is driven by token probability. The deterministic state transition is replaced by a range of potential outcomes, most of which are uncalibrated and unpredictable. Asking an LLM to check its own work doesn't solve this. The verification step simply inherits the same probabilistic flaw as the generation step. The semantic space is too vast to govern with prompts or context engineering alone. You cannot prompt your way into absolute reliability. To safely deploy generative agents, we must stop trying to make the LLM itself deterministic. Instead, we need to build a hard, external control boundary around it. This control crisis mirrors the configuration management challenges of the late 1990s. Back then, systems were becoming too complex to manage with simple scripts that assumed everything worked as intended. The solution was promise theory. It posits that you cannot force an agent to execute an action perfectly. It can only promise to try. The responsibility for success lies in continuous external verification that the promise was actually kept. We can map this challenge across the trust verification landscape. Traditional planning and raw generative agents sit in the bottom quadrants, assuming output is correct without checking. The dual-state architecture moves the LLM into the top right quadrant, applying continuous external verification to stochastic generators. This creates two distinct spaces, a deterministic workflow state controlled by the engineer and a stochastic environment state inhabited by the LLM. By separating the workflow from the generator, control moves from the probabilistic model to the deterministic system. We no longer rely on the LLM to act correctly. We rely on the evidence it produces at every step. This link between the deterministic and the stochastic is maintained by a mechanism called the action pair. It is the atomic building block of a bounded agent. The base case action pair follows a strict loop. It begins deterministically. If a precondition fails, the process halts. If satisfied, the LLM generator produces output. This output must pass a deterministic guard, the control boundary. If it fails, failure details force the LLM to retry. The action pair ensures the overall system remains deterministic, even though the generator inside it is chaotic. In a sandbox, you can simply discard a bad LLM output, but when executing live sysadmin commands, like restarting a server, you simply cannot just undo a failed action. To solve this, the architecture uses an effector extension for actions that permanently change the environment. Real-world actions are wrapped in a four-phase transaction. The forward action, or effector, is flanked by two distinct guards. The pre-guard validates the plan's logic before it's executed. The post-guard senses the actual system outcome afterward, ensuring the command achieved the intended state. This dual-guard structure allows AI to manipulate real-world infrastructure without the risk of an uncontrolled failure. These principles are applied in CHOPS, a proof-of-concept voice-controlled framework for systems administration. The first challenge of a voice agent is intent, taking an ambiguous human phrase and routing it to the correct deterministic workflow. Using an LLM for initial routing is a bottleneck. In tests, LLM classification took over 2 seconds, with only 87% accuracy. Moving classification outside the generative space solves this. An embedding classifier routes commands in just 29 milliseconds, 80 times faster with higher accuracy. This meta workflow identifies and dispatches the task before any generative AI is ever touched. By isolating intent classification, the system reduces latency and ensures the LLM is only triggered for the specific generative tasks it was built for. The ultimate test for this architecture is a test-driven development workflow, especially when a user forgets to provide a goal. An unconstrained LLM agent would react by hallucinating a task, like inventing a text summarizer, just to keep the conversation going. The dual-state agent takes the opposite approach. When the precondition guard fails because a goal is missing, the system halts. It refuses to guess, and instead triggers a deliberate escalation to the human operator. The user is forced to provide an explicit specification, such as run stack TDD, before the workflow is allowed to resume. The process is tracked in an append-only repository of every pass and escalation, represented as a directed acyclic graph. This causal chain enables intelligent backtracking. If a leader stage fails, the system traces up the graph to rewrite tests using that specific failure context. This strict evidentiary chain eliminates hidden state. Every action is traceable and verifiable, which even allows reinforcement learning systems to navigate these workflows safely. Confining generative models inside this rigid dual-state architecture provides a hard limit on what an AI can do. It aligns capable but incoherent output with the deterministic standards required by the enterprise.